Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 37 Organic Chemistry 1. Today we will continue on structure, synthesis and reactions of alkenes, polymerization of alkenes. A polymer is a large molecule composed of many smaller repeating units called monomers bonded together. Alkenes serve as monomer for some of the most common polymers, such as polyethylene, polypropylene, polystyrene, and polyvinyl chloride, and many others. Alkenes polymerize to give addition polymers resulting from repeated addition reactions across their double bonds. Addition polymers generally form by chain growth polymerization, the rapid addition of one molecule at a time to a growing polymer chain. There is generally a reactive intermediate, cation, anion, or radical at the growing end of the chain. Many natural materials such as protein, cellulose, and starch, and complex silicate minerals are polymers. Artificial fibers, films, plastics, semi-solid resins, and rubbers are also polymers. More than half of the compounds produced by chemical industry are synthetic polymers. Cationic polymerization. Cationic polymerization is applicable to vinyl monomers having electron-rich double bond. The electron-releasing inductive influence of alkyl groups causes isobutene to polymerize very quickly at low temperature, where propylene reacts insufficiently, and ethylene is practically inert. For similar reasons, alpha-methylstyrene is more reactive than styrene, and substitution of an electron-withdrawing halogen for an ortho or para halogen decreases the monomer reactivity still further. As corollary, ortho and para electron releasing substituent RO, RS, aryl increase cation stability and monomer reactivity. When pure isobutylene is treated with trace of concentrated sulfuric acid, protonation of alkene forms a cation. If a large concentration of isobutylene is available, another molecule of the alkene may act as nucleophile and attack the carbocation to form dimer and give another carbocation. The chain will keep adding across more molecules of the monomer. The polymer of isobutylene is isobutyl polyisobutylene, one of the constituents of butyl rubber used in the inner tube and other synthetic rubber products. Isobutylene or isobutene acidified with H plus protonated to form carbocation. This carbocation will be attacked by another molecule of isobutylene to form dimer. Then another one comes in, trimer, etc., until we form polymer chain. The termination step will be that the sulfate ion will act as a base and abstract the terminal hydrogen, from the terminal unit and form alkene, and the carbocation will disappear and the reaction will stop. We give this structure for isobutylene since the first and the last species, we can neglect their structure, the isobutene final unit and the butyl first unit, and we just write the isoBTH2C has 2CH3 between brackets n and n number of repeating units. Boron trifluoride is an excellent catalyst for cationic polymerization because it leaves no good nucleophile or base that might attack a carbocation intermediate and end the polymerization. Boron trifluoride is electron deficient and a strong Lewis acid. It usually contains traces of water, and the trace of water will act as a co-catalyst by adding to and then protonating the monomer, the alkene. So acid-base, Lewis acid-base catalyst formation followed by protonation, proton transfer to form the carbocation. This is initial step, and giving this anion, and this anion is not a good nucleophile or a base. So here we have this initiator will go on and go on and go on, giving a high molecular weight polymer. Styrene carbocation will be attacked by another styrene monomer to form dimer carbocation, trimer carbocation, etc., until we get the polystyrene. To terminate the reaction, one of the styrene molecules will act protonated from this hydrogen adjacent to the carbocation to form a terminal alkene and start another carbocation to form a new chain. Polystyrene is used in a wide range of applications such as packaging, household appliances, consumer electric products, building and construction, for example, insulation, foam, panel, bath and shower units, lighting and plumbing fixtures, medical items such as tissue culture trays, test tubes, battery dish, diagnostic component, and housing for test kits. As we can see, isobutene forms high polymer very fast because upon protonation it gives tertiary carbocation which is stable and the reaction is fast. Propylene yields low molecular weight polymer, while ethene is practically inert in cationic polymerization. Alpha-methylstyrene again form highly stable carbocation, more stable than the cation formed upon the protonation of styrene. And when we have the electron withdrawing group like chloride group on the aromatic ring, decreases stability of the carbocation formed on this carbon, making the parachlorostyrene less reactive. Anionic polymerization, like cationic polymerization, anionic polymerization depends on the presence of a stability group. In this case, to stabilize anion, double bond should have a strong electron withdrawing group, such as carbonyl, cyano, and nitro group. Methyl alpha cyanoacrylate contains two powerful electron withdrawing groups, the carboxylate group and the cyano group, and it undergoes nucleophilic addition very easily. So treating this one monomer with trace of base form carbonyl, and then the carbonyl will act as a nucleophile, add to another monomer unit to give dimer anion, trimer anion, etc. until we get polymer. We can end that by adding drop of acid or pour the reaction mixture or acidified water or any protic solvent which has hydrogen to give the polymethyl alpha methyl acrylate for that monomer. Polymethyl methacrylate, PMMA, the abbreviation of this polymer, a synthetic resin produced from the polymerization of methacrylate. A transparent and rigid plastic is often used as substitute for glass in products such as shatterproof windows, skylights, illuminated signs, and aircraft canopies. Free radical polymerization. Many alkenes undergo free radical polymerization when they are heated with radical initiators. For example, styrene polymerization or polymerizes to polystyrene when it is heated at 100 degrees Celsius with peroxide, very small amount of peroxide as initiator. So the peroxide will give free radical, and free radical will add to the styrene unit, forming monomer active radical, which react with another molecule of styrene to form dimer radical and keep going to give polymer. In this case, the chain growth may continue with adding of several hundred or several thousand styrene units. Eventually, the chain reaction stops either by coupling two chains or by reaction with an impurity such as oxygen, or simply running out of monomers. Coordination polymerization is a form of polymerization that is catalyzed by transition metal salt and complexes. Coordination polymerization started in the 1950s with heterogeneous Ziegler-Natta catalyst based on titanium tetrachloride and organoaluminum co-catalyst. The mixing of titanium tetrachloride with trialkyl aluminum complexes produces titanium 3 containing solid that catalyzed the polymerization of ethene and propene. Following the catalytic design, it was found that polymerization of alpha olefins resulted in stereoregular structure, either syntactic or isotactic, depending on the catalyst used. We will get to know what's that mean, syntactic and isotactic and atactic. Reaction of titanium tetrachloride with triethyl aluminum gave complex structure where the catalyst system still have empty orbital ready to coordinate and react with alkene unit to form complex 4-member ring transition state where the ethyl group transfer to this carbon and titanium carbon bond is established here, leaving empty orbit again. They exchange the alkyl chain and the empty orbit exchange the position So this will be in here, and the chain is going up. Another unit of alkene group will come and coordinate again with titanium, and the chain alkyl group will transfer to this carbon, growing up the chain here, migrate up, and this will go down again, ready for another unit, and so on. This provides isotactic polymer where all R groups are in the same direction of the polymer backbone. When we use vanadium tetrachloride instead at minus 78, using aluminum isobutyl chloride and phenoxide and toluene, syntactic polymer was obtained. R is up, R is down, R is up, R is down, switching up and down. When titanium tetrachloride, diethyl aluminum chloride, and dibutyl magnesium catalyst provided what we call it atactic polymer, substituents are placed randomly along the chain. This topic was the subject of Nobel in 1963 in chemistry. Ring opening metathesis polymerization. Ring opening metathesis polymerization, ROMP, is a type of olefin metathesis chain growth polymerization. The driving force of the reaction is believed ring strain in cyclic olefins. Reaction of alkylidene metal with cyclic alkene via 2+2 cycloaddition reaction provide this intermediate which ring open to form new alkylidene metal, reacts with another unit again to form four-member ring, open up, form a new alkylidene metal. As you can see, the grow up of the chain to provide metal. This is the structure of one type of catalyst used in this reaction. See you in the coming lecture. Bye-bye.